Hi everyone, my name is Connor Valentine. I work with Professor Lynn at Carnegie Mellon University. Today I'll be presenting my presentation, Shear Processing of Diblock Polymer Liquid Crystals to Achieve Rapid Equilibrium States. So the system that we'll be talking about today is a neutral diblock polymer where the blue block is soluble in water and the yellow block is not. Now when we concentrate these, we get the formation of micelles where the yellow blocks are actually just an alkane core, and the micelles are about 3 nanometers in length or in diameter. So when we begin to concentrate these micelles, we can get the formation of structures such as hexagonally packed cylinders, body center cubic if they're spherical, or face center cubic. Now, in this system, we also have the formation of a Frank-Caspar A15 phase. Now, Frank-Caspar phases were originally discovered in metallic systems in the 1950s. And in the last 10 or 20 years, people have begin to see them in a variety of soft materials, which is interesting. And sometimes they mimic similar findings that were originally found in metals. Now, on the left, we have a body center cubic phase. On the right, we have a Frank-Caspar A15 phase. Now, at first, this looks kind of complicated. Let me pull up my laser pointer. At first, this looks complicated, but if you look closer, you can see that the A15 phase is actually just a body center cubic lattice where you have a micelle in the middle and one at each corner. But in the A15 phase, you also have these two micelles on each face of the unit cell. So you could imagine that this would be a little bit more brittle than the body center cubic phase, just because there's less sliding planes, it's more compact, there's more going on in one unit cell. Okay, so the reason that processing these systems is important is because by processing them, we can achieve the properties you want. And an example I like to talk about is metallic turbine blades. Now, you can see here several steps in the path to a complete crystal blade. At first, they made polycrystalline blades, as you can see here, and it was found that grain boundaries actually expand more than the crystal itself. And when you have expansion, you lose efficiency. So the next step was to make very long stretched grains. And you can see each one of these is actually a crystal grain, where you have a continuous crystalline lattice without a boundary or defect or rotation. Now, a modern turbine blade, we can actually make them into a complete single crystal. So over here, this blade is one crystal, and as a consequence of this transition, we have a huge increase in efficiency, which has driven advancements in everything from airplanes to power generation, and that's a huge deal. So with soft material, the modulus is a lot lower, right? Orders of magnitude lower. And so we have different process abilities other than extreme thermal annealing procedures, where we can shear them, we can make them into a nice layer, and this will affect our crystal structure. So the specific system that I'll be talking about today is Bridge 58 in water. Bridge 58 is a simple surfactant molecule where you have an alkane tail that's about 16 carbons long, and you have a polyethylene oxide tail that's 20 units long. So you get this phase behavior on the right. We have temperature and weight percent of the polymer. Now, you'll see some of those phases I just talked about: face center cubic, body center cubic, hexagonally packed cylinders, and also Frank-Caspar A15, in addition to a disordered phase that you see over here, where there's no more crystalline structure. It's more like a liquid micellar state. What you don't see on this is that the authors reported that in this window, when you cool from hexagonal cylinders down, there's a Frank-Caspar sigma phase that's accessible via thermal annealing procedure. Now, in addition to this complicated phase behavior on the path to equilibrium, you have concentrations that are relevant to processing, and so this is a region of interest for us to explore, so we understand how to work with these materials and get the phase behavior and the properties we want. Now, this is the thermal annealing procedure that the authors in that paper used. Now, when you heat to 60 degrees C, you have cylindrical micelles, and as we begin to cool, will quench to 25C using liquid nitrogen boil off, so it's pretty quick. And after a few minutes, you have a body-centered cubic phase. A few hours, you have this Frank-Caspar sigma phase come in. It's going to take you about 5 months until you have a complete Frank-Caspar A15 structure, and that's the equilibrium phase. Now, what I'll be going to show you today is that using shear processing, we can shorten this time frame from months to minutes. And we're going to skip this Frank-Caspar sigma phase entirely in the process. So what we did is we took our samples to Argonne National Laboratory, to the Advanced Photon Source, and we put our samples into a shear cell where we can oscillate back and forth. And we're going to send X-rays down the gradient of shear, and they're going to scatter on this detector. I understand not everyone understands how scattering experiments work, or small angle scattering. So I'm just going to take one slide to explain what's going on. What we're going to do is take detector images every 5 seconds. So it's basically like a photograph. And we're going to radially average along this vector Q, which is just radius from the center point along this flat plane. Now, you could see here if we did that, we're going to get this profile. You can see these 3 really bright peaks, right? Well, these are those 3 bright peaks you see here. So, get these peaks. How do we determine the structure? Well, we can compare them to known spacings of other phases. I'm not going to get into how we do this, or you can also calculate the expected positions for different structures. But for the purpose of this talk, let's just say we're comparing them to known spacings of BCC, A15, the hexagonally packed cylinders, and a sigma phase, Frank-Caspar sigma. And we can just compare the lines, we can slide them around, and we can use MATLAB to get a match for which phases are in each snapshot. And over here, you can see we have a nice Frank-Caspar A15 phase that we saw during the experiments. And the first 11 peaks match great, and you can actually match these 2 to the references. So if we're studying these phases over time, we want to know the relative amounts of them. And for this system, there are 3 different peaks that are like, so a peak here in BCC doesn't overlap with the other phases. We have an A15 peak that doesn't overlap, and a sigma phase that doesn't overlap. So I'm going to say each of these are unique peaks to each of these, and we're going to track the intensity of our unique peak throughout over time and get a metric of formation that way. Now, this method only works where you're tracking one peak at one Q position, because we're not changing the polymer, the concentration, or the temperature. So we know that we can look for a peak here, and if there's a peak there, it's probably just an A15 phase, or at least partially an A15 phase. Now, here's our control experiment where we just have the crystal formation at 25C after the thermal annealing procedure without shear. You can see that BCC just comes in, stays there. It's pretty boring, right? It's our control experiment. Now we're going to start shear at T equals 0 for the next phase, for the next slide. Okay. So you can see this is counting down. We're going to apply oscillatory shear at 0 minutes. All right, and you can see that the sample rapidly changed to an A15 phase in a matter of about 1 or 2 minutes. Now that's a drastic change from 5 months. I'm just going to let this roll over and play again. And you can see that as we approach 20 minutes, the Frank-Caspar A15 phase is pretty happy. And now, okay, we're back to the start of the GIF. We're at BCC. We're going to start oscillations now. And the A15 phase comes screaming in. Now that's a pretty big find. You can see that when we plot this as intensity versus time, you have thermal equilibration alone on the left, and you have Laus processing on the right that starts here at 0. And you can see that BCC drops dramatically and A15 comes in. Now this is under different oscillation conditions. So how are we going to compare them? Well, we're going to apply an Avrami type fit, the Mel-Johnson-Avrami equation, where you take your intensity and you fit it to the stretched exponential, where you have 2 parameters, b and n. Now, if you zoom out, this is basically just a stretched exponential fit, and we're just focusing on pulling out a time scale using this fit. Normally, you could try to get a growth mechanism and other information, but for this talk, we're just focusing on that time scale, tau. Now, if you take these two fit parameters and you get tau, which is a unit of minutes. So that's what I'll be talking about. Okay, so here's the intensity versus time data for that first experiment video I showed you. After the thermal annealing procedure, we have BCC, at time equals 0. We start shear. A15 comes screaming in, and you can see that our Avrami fit captures a lot of the behavior fairly well. And we have a time scale of about 2.3 minutes for the A15 formation to take place. So when we investigate the effective strain amplitude at the same frequency, 1 Hertz, you can see that as we increase the strain amplitude, the A15 formation occurs faster. And our Avrami fits hold pretty good. And this was a good result. We were happy to see this. So what surprised us, though, is that by lowering the frequency at that largest strain amplitude, we actually saw a suppression of A15 entirely throughout the duration of the experiment, where we actually only just had BCC. And the reason this intensity dropped is because the peaks broadened a lot. So the intensity drops and the peaks broaden, which tells me that the grains are getting very small during this shear. The crystalline grains are getting very small. So if we look at this lower frequency, 0.1 Hertz, you can see that as we increase the strain amplitude, we get the opposite effect. And actually our time scale is getting longer and longer until it's actually longer than the duration of the experiment. We only have a limited amount of time at the beam line. So here we have two different GIFs on the left. On the right, we have different shear conditions. And you can see that under these conditions, we don't have any A15 forming at all. And on these conditions, we only have A15 forming. So we're able to tune our oscillation parameters to get the phase behavior that we're looking for, at least the transition rate that we're looking for. These are the two extreme cases that we found during our experiment. Now, what I'm not telling you is that these are actually at the same strain amplitude, 1,770%. But on the left, we have 0.1 Hertz frequency, and on the right, we have 1 Hertz frequency. And these frequencies are actually pretty close together. So what I'm going to do is I'm going to take all this time scales from the Avrami fits from all the different shear experiments we did, and I'm going to plot them on this graph where we have just on strain percent on the bottom axis. And we have our 10 Hertz samples in blue, 1 Hertz in red, and purple Hertz, 0.1 Hertz in purple. And this arrow I'm going to plot here to show the scenario where we didn't observe any A15 formation on the duration of the experiment. So I'm going to argue that the time scale here is much longer than 100 minutes. So I'm a chemical engineer, so we're going to try to normalize these. Now, when we plot the data against the maximum shear rate during oscillation, which is just basically the frequency times the strain amplitude, we get this trend where the high frequency and intermediate frequency data roughly, follow this empirical trend line with the slope of minus 0.5. However, the low frequency data do not follow this trend. So what this tells me is that there's, competing timescales for the formation of Frank Caspar A15 from this metastable BCC state. Now, this is a balancing act, right, between what phases are stabilized during shear and what phases are not. So when you start shearing the sample, you're going to have an increase in intermicellar collisions, right? You're sliding these layers between each other. Now, I think that's increasing the rate of chain exchange where the molecules can then jump between each other. And if the conditions are right, this will help us get to our prerequisite aggregation numbers for A15 formation a lot faster. Now, I think what's happening with our low frequency case is that we're approaching steady shear conditions because it's like very low and slow. Now, this might be preventing us from reaching an A15 phase because it's easier for the layers to slide past each other in BCC. So Thanks for listening to my talk, and I hope you have questions in the virtual session or whatever is going on with this meeting. Thanks for listening. Oh, I got to end the recording.